Okay, so let us start. So last time, at the end of lecture, we discussed relativistic generalization of the cross-section. So we want to derive a relativistic generalization of the cross-section from some initial state to some final state. Okay, so initial state denoted by alpha is denoted by alpha, the final state denoted by beta. So we will, for most physical process, we will consider two particle scattering. So this is just two particles and then scatter. Okay, so this is our initial state. Always only have two particles, but the final state can have arbitrary number of particles. Okay, can have arbitrary number of particles, and then we define. So we require that d sigma alpha beta to be Lorentz invariant. Because the probability for they should not depend on say your frame. We also want to define to be symmetric in 1 to 2. Okay. So to make connection with the non-relativistic story, we can consider the rest frame. Say as a starting point, we can consider the rest frame of particle 2. Okay, you can always go to the rest frame of particle 2. And then in that frame, then we can define this quantity to be the probability per unit time from alpha to beta dt, and then divided by the incident flux of particle 1. Okay. So so this d p alpha beta t is the probability. Let me just write it. So this is the probability per unit time for this process from alpha to beta. Okay, and then the dn1 dt dA would be the incident flux of particle 1. Okay. So this expression is a lateral generalization to relativistic context, which in the rest frame of particle 2. Okay, in the rest frame of particle 2. And so our strategy is to first work out this quantity in the rest frame of 2, and then we use the Lorentz, the requirement of the Lorentz invariant and the symmetric in 1 and 2 to write it in the general frame. Okay, so that's our strategy. Okay. And so first let's talk about this quantity, this probability from alpha to beta. So we have so probability from alpha to beta. So can be, so by definition is defined as the following. Is we want to look at the transition amplitude, which give you the beta state at time plus infinity, and from alpha at time minus infinity. Okay, so this is the amplitude, and then we take the square. Okay, and then we divide by the normalization of the beta itself and the alpha itself. Okay. Okay, we divided by the normalization of the beta and alpha, the state themselves. Okay, so that the whole thing really define the probability. So the upstairs, we already defined before. So previously we defined the beta plus, infinity, alpha minus infinity. So this is by our previous definition. It's given by 2 pi to the power 4 delta p alpha p beta. So the p alpha p beta is the total momentum of the initial and final states, and the times m alpha beta. Okay, m alpha beta is defined to be the scattering amplitude from alpha to beta. Okay. Okay, so this is what we this was essentially our definition of the scattering amplitude. Yes.
Can you remind me? So the plus infinity minus infinity, is that in like space time or just time?
Time, yeah. Yeah, means that the t equal to minus infinity. Yeah, so this is the Heisenberg state, okay? So this is the Heisenberg picture. So this means that at the t equal to minus infinity, we have a free particle state described by alpha, and at the t equal to plus infinity, we have free particle state defined given by beta. Other questions? Okay. So now let's take the square. Okay, now let's take the square. So remember, so the reason we need to put in downstairs, you say, why do we need to put it downstairs? Because are they supposed to be normalized? Okay, but in practice, when we do the calculation, or in practice, when we talk about the free particles, we use the plane wave basis. Okay, but plane wave, remember, is not normalizable. It's only normalizable as a delta function. Okay, so their normalization is not equal to 1. Okay, it's actually so we have to be careful. Okay, so that's why we need to include them here. Okay. So yeah. Good. So now let's look at this quantity square. So let's just move it down. So to save time, I just don't copy it. So this quantity square, then just equal to right-hand side square. Okay, so we will have 2 pi for the delta function square, and then we have f of m alpha beta square. Okay. And now let's look at the delta function square. So the delta function square will have 2 pieces. So the so the delta function square okay, and let me just save time. So this square, then we can take one piece, one copy of it. We just write it as p alpha minus p beta. And then the other piece will be just delta 4. We can just evaluate at 0. Okay, because we already set the p alpha equal to p beta from the first delta function. Okay, so the second factor can be just become delta 0. Okay, so now we know how to. So we have seen this before, right? So what is this object? Do you remember? Yes? Yeah, it's the total space-time volume. Okay, the reason is that the 2 pi delta 4 0. So this is a 0 in momentum space. Okay, so this is just equal to d4x expansion ikx evaluate at k equal to 0. Okay, evaluate at k equal to 0 because this is giving you the 2 pi delta k. And so you evaluate k0. When you evaluate the k0, then of course this is just the space-time volume. Okay, so I take the spatial volume to be v, and then this is t is the time period. Okay, so so physically you can interpret the t as the duration the time duration we actually do in the experiment, okay, because only that part is relevant for our experiment, okay. So this capital T can be interpreted, yeah. Okay, good. And now we can just replace here. So now we can just replace here by V times T, okay? Okay, we can just replace here by V times T, okay? So now let's look at the downstairs, okay? Now let's look at downstairs. So downstairs, so the alpha and the beta would be just say, yeah, so the typical alpha. So the alpha state would be say if your initial momentum is P1 and P2, okay, it would be like this. For scalar particle, just will be specified by P1 and P2. And if you have polarizations, then there will be polarizations. Okay, here I just give you an example. So now if you look at the normalization of this kind of state, okay, remember the P1 and P2 defined. So remember if you have a single particle state of momentum P, so that is normalized to be 2 pi cube 2 P0 delta 3 P minus P prime. Okay, because they're always on shell. Okay, initial and final state they're on shell. So P0 are functions of P. Okay, so that's how. Yeah, we normalize them. So P is normalized by square root omega k omega P, say AP acting on 0. Okay, and for example for scalar particle, and then you look at the normalization just like this. Okay. So now if you look at the P with itself, okay, then you have P equal to P prime, and then you have essentially just have 2 P0 times V. Okay, the V is the spatial volume. Because here you just have 2 pi cube, the delta 0, and delta 0 is in the spatial momentum. Okay, and spatial momentum, for the same reason, just gave you the spatial volume. Okay. And so, yeah, and so now we can just apply this to alpha and beta. So the alpha, so if I take the alpha to have momentum P1, P2, to consist particle momentum P1, P2, and beta to consist of momentum, say, K1 and Kn, suppose they are n particles, okay, so n can be arbitrary integers. And then from here, then the alpha which itself would be just 2E1 times volume and 2E2 times volume. Okay, E1 and E2 are the energy of the P1 and P2. Okay? Yeah, so E1 is equal to P1, 0, okay, and E2 to P2, 0. And similarly, the beta would be take the product J from 1 to n, 2 Kj, 0th component, times V, okay? Okay. So and so the K0, Kj0, yeah, for example, just Kj0 just equal to Kj square plus Mj square. Okay, so different. So here we allow the different particle to have different mass. Okay. And yeah, similarly with P1, 0 and P2. Okay. So now with those preparations, now we can write down dpt. So now the dp alpha to beta dt, then essentially just equal to p alpha beta divided by t, the total duration of your the physical process. And so the reason they just related, you say how can you do this? Okay, this is a differential, and how can you just divide it by the t? Do you know a reason why we can just divide by this? Yes.
Well, presumably, if like the probability was small or something, like you would just expect it to like kind of go up linearly in time.
It's just because of that's a good statement. But the statement I was wanted to you say is that the because of the time translation symmetry, and so you would expect that the probability per unit time should be independent of time, and so the probability say for duration of time, and you can just multiply by the total time. And indeed, in order to make this equation make sense, of course, the p have to be small because otherwise, if you multiply, this thing has to be small. Otherwise, when you multiply by t, of course, it will be greater than 1. Okay, but just to divide by t is from the time translation symmetry. Okay. Okay, so this is good because we know here from the delta function there's a factor of t. Okay, there's a factor of t. So if we combine everything together, and then we can just then the upstairs is given by. So we have the 2 pi power 4 delta 4 p alpha p beta. Then m alpha to beta square times vt. And when I divide by t, and then this t go away, okay, so I can just erase this t. So this is upstairs, and then divided by t, a capital T. And then the downstairs, we just copy these two expressions. Okay, downstairs, I just copy this expression and this expression. Okay, so this is the 4 E1 E2 times V square, and then J from 1 to N to K0, Kj0 times V. Okay. Good. Yes.
So you're now taking T to be the total time of your experiment. Are you taking V to be like the volume of your experiment, or? Yeah. Of your detector?
And no, it's not the detector. It's just we're computing S matrix, right? So S matrix, you always assume you wait for a long time so that your initial state is free and your final state is free. Yeah. Of course, it's much not. It's the range of your detector. Yeah. Yeah. You have to put the detector very far away in order to measure the particle. Yeah. Yeah. You can imagine the V just essentially is the volume which the experiment is happening. Yeah. Other questions? Good. So you see there's all this V flying around. Okay, so they look very unpleasant, but don't worry. Later, if you are doing the right thing, then all these unpleasant things will go away. Okay, so that's the rule of physics. And in the intermediate step, you may see a lot of unpleasant things, but if you are doing the right thing, okay, and then all this unpleasant thing will go away, or you say, oh, then I must be doing the right thing. Okay, so here, actually, this probability is not the probability we actually measure, because here I assume that the final state, here I assume the final state, here I assume the final states have precise momentum K1 and Kn. Okay, so in reality, of course, we will not be able to make the precise measurements. Okay, so in real experiment, we always detectors have some finite extension, have finite detectors have finite resolutions. So what we measure is actually when we say the particle, say, have momentum k1, we actually means that the particle 1 is within some decay 1 around A1, around K1, okay? So there's always some finite neighborhood of K1, which are allowed by the detector resolution. And similarly, in reality, it's particle 2 in dk2 around K2, etc. Okay, so the particle n, dkn around Kn. So then we actually need to integrate over all these resolutions, okay? So that means that we should multiply this dpt, okay, this corresponding to sharp final momentum, okay, sharp final momentum, and we should multiply by those uncertainties, okay? So that means that the, say if I take this equation to be star, this equation to be star, so the one actually is measured by the experiment. When we say T alpha beta dt from the real experiment, is actually corresponding to the star times, okay, those uncertainties around the so j equal to 1 to n d3k j 2 pi cube. Okay, so we need to multiply the number of states, okay, the number of states within each this decay momentum space volume, okay. So the number of the states, and the number of states is given by this times the volume, okay. So do you remember where this volume comes from? Yes?
Like the density of states?
Exactly. So this gives you the density of state. It's because the, so if I just remind you, remember if you, so the way to think about it, just imagine you put your system in the box, and then your energy level will be quantized in terms of 2 pi, say 2 pi cube divided by the volume. Okay, so this is the number of states in momentum space, the density of states, and then you multiply by that decay. Okay, multiply that decay. Good. Okay. So this is actually the quantity we are interested in. Okay, this is the quantity we are interested in. Any questions on this? So now let's just plug in that star into here. Okay, so now the nice thing, now we can count the number of V's. Okay, if we are doing the right thing, all the V should cancel. Okay, except yeah, but not quite yet. Okay, so upstairs we have 1 V. Here we have V squared. So let's first cancel this V, so that we don't have to worry about that. Okay, so let's first cancel that V. And now we have, downstairs we have V for each J. And upstairs, now we multiply this by this, and then for each J have 1 V. So all this V will cancel that V. Okay, all this V will cancel that V. So we left with only this single V, okay? This single V. So now we can write it the following. So I can write it this f m alpha beta square. So I just copy this. And then I divide it by, let's keep this, divided by 4E1, E2 times V. And then I group everything else into what I call d mu. Okay? And d mu is everything else. D mu is defined to be this delta function. And then j from 1 to n, d3k j 2 pi cube 2kj 0. Okay, so I just combined these two products. Okay, combine these two products. Okay. So the nice thing, the reason I group all this together, because now d mu now is Lorentz invariant. Okay, so this is a Lorentz invariant measure. Because you remember, this is Lorentz invariant. And remember, this combination is also Lorentz invariant from your first day, essentially in QFT. Okay, in your first P set, you were, yeah. So now this nice thing is that this now is a Lorentz invariant. Okay. So now we have this nice expression. Okay, we have this nice expression. We have this by definition is Lorentz invariant. And then we have this 4E1, E2, and times V. Okay. 4E1 times V. Okay. And now we want to write them into a Lorentz invariant way. Okay. But we haven't done it. This is only upstairs. This by itself is not Lorentz invariant. We have to divide it by the downstairs. So the downstairs is the flux. Okay, is the flux. So now in the rest frame of particle 2, so let's calculate the flux of the particle. So the flux of the particle, okay, so the flux, so we need to calculate the flux of particle 1. So that's the thing we need to divide. Yeah, so this is the flux of the particle 1. Okay. So that flux is the number of particle per unit time and per area. Okay, per unit time per area. So this is the same as the number of the particle, number density of the particle 1 times the velocity of the particle 1. Okay. So remember, the flux is essentially the density times the velocity. Okay. So this gives you the number of particles per volume, and this is give you the distance traveled per unit time, and yeah, so together they give you that. Okay. And so yeah, so this is the velocity. So this is the density of particle 1. So this is all in the rest frame of particle 2, okay? Okay. So now in this experiment, we have 2 particles scattering. So what do you think will be the density of 1? So what do you think is the N1? Yes? Exactly. How many particles do we have? We only have 1 particle. so this is just given by 1 over V. Okay? So this is just given by 1 over V. So now we can find the d sigma. Okay, so the d sigma alpha to beta then is defined to be dp dt. Okay, now divided by the flux of 1, particle 1. Okay, so now this is just given by, now the volume cancel. Okay, because n1 is 1 over volume, and then there's a volume here, and now finally this volume cancel. Okay, so now if we divide that by the flux and the volume cancel, and then we get m alpha beta square d mu, and then divided by E1, E2, and V1. Okay, the velocity of the particle 1. Okay, so this is the so V1 of course can also be interpreted as a relative velocity between 1 and 2. Okay. Anyway, so this is the expression we find. So this is the expression in the rest frame of particle 2. Okay. So by definition, we want this thing to be Lorentz invariant and symmetric in 1 and 2. Yes?
I was thinking like regarding the cancellation of the 1 over v factor.
Yeah.
Is like another way to interpret it, like you think of, instead of a plane wave, like a narrow wave packet or something centered at K1.
Yeah.
So you get like a v from the wave packet sensitive states, and that would cancel. Is that valid?
Yeah. I think it's the similar idea. Yeah, because let me see. Because essentially you get rid of that v. Yeah, when you consider the wave packet, then you get rid of this v. Yeah, and then you also get rid of this v. Yeah. So just get rid of the v, one upstairs, one downstairs. Yeah, that's right. Yeah. Good. So now we want to write this in the Lorentz invariant form. So this is emphasized. This is in the rest frame of 2. So now I look for object. So now I want to look for object which I will call it sigma. So sigma is Lorentz invariant. Yeah, sigma, let me write here. Sigma is Lorentz invariant. And symmetric in 1 and 2. And in the rest frame of 2, then the sigma become this downstairs become this E1, E2 times V1. Okay, so this is not a manifest Lorentz invariant object. Okay, it's also not symmetric in 1 and 2. But I should be able to find an object, sigma, that is by itself is Lorentz invariant, symmetric in 1 and 2, and in the rest frame of 2, reduced to this object. Okay, if I can find this object, then I'm done. Okay, in finding the cross section, yes.
Should there be a factor of 4 in the denominator?
There should be a factor of 4. Yeah, there should be. Thank you. Yeah. Yes, some other questions? Good. So I want to look for this object sigma, okay? And so you can do a little bit trial and error to find such a sigma. So I will just write down the answer for you, okay? And to save the trouble. I could have put it in your p-set, but I decided not to do it. So turned out the sigma is given by. So when you write down the answer, it's very simple. You can almost guess it, okay, in the sense. So it's P1 dot P2 square minus M1 square times M2 square. Okay, M1, M2 are the mass of the particle 1 and 2. Okay? So this object satisfies these 3 conditions. Okay, this object satisfies these same conditions. Also, I will leave the exercise for yourself to check it. Okay, it's very easy to check it. So you just go to the right frame of Q, and then you can check this reduced to that. Okay. Good. So now we almost have our final answer for the cross section. So the d sigma for this 2 to n scattering So now we just collect our final result. So we have the sigma alpha beta now is equal to m alpha beta square d mu divided by 4 sigma, okay, just d mu. Okay, so this is just our final answer. And the sigma is given by that guy, okay? Capital sigma just given by that guy, okay? And so this is manifest Lorentz invariant. And the manifest symmetric on the 1 and 2. Okay, because sigma is obviously symmetric on the 1 and 2. Okay, and yeah. And this is a very beautiful formula. Okay, even though we went through a lot of trouble, went through a lot of V's and T's, but in the end we get a very beautiful answer. Okay, yeah. Good. So now let's consider some kinematic regimes of this formula. Okay. So now let's talk about some kinematics of this formula. So it's convenient. So we have two particles, two initial particles. It's convenient to introduce the center of mass energy for the full system. So we can define something called S, small s. Okay, this is not big S. So big S is reserved for action. So this is small s, P1 plus P2 squared. Okay. So P1 and plus P2 is like the total momentum of your initial state. Of course, it's also total momentum of your final state, just from the momentum conservation. And then if I look at P1 and P2 square, and then this is just essentially the invariant mass for your full system. Okay. So this S is square root S is the invariant mass. It's the effective mass of the whole system. Yeah, of this. But when I say the whole system, I just mean the whole system of particle 1, particle 2, and also the final states. Okay. Okay. So we can also write this sigma. Turns out we can actually write sigma in terms of S, because the because P1 dot P2 can be written as 1/2 P1 plus P2 square minus P1 square minus P2 square. So this is just M square. So P1 square just minus M1 square. P2 square just minus M2 square. So this is just equal to minus 1/2. Okay, S. Sorry, should be total. S minus M1 square minus M2 square. Okay, so P1 P2 square just equal to minus S. Okay. And then the sigma just can be expressed in terms of that. Okay. So the sigma. So let me just write down the final expression for the sigma in terms of S, just equal to square root S square 2S M1 square plus M2 square plus 1 square minus M2 square. Okay, so this whole kinematic factor of sigma can be just expressed in terms of S. Okay. Good. Any questions on this? Okay. Good. So so now let's another thing is that often we even though this formula can be used in any frame, but sometimes depending on your question, the expression is simpler in some frame than some other frame. Okay, so one of the very frequently used frame is so-called the center of mass frame. It's called the center of mass frame. So in the center of mass frame, essentially is that in this frame that the total center of mass of the system does not move. Okay, so it means that the total momentum in the center of mass frame, total momentum, let me say, the total momentum equal to P1, P2 is taken to be 0. Okay, so the whole part, so the full system is not moving, and so that means we can take, so means that P1 equal to minus P2. So equal to let's call it PCM. Okay, just means the center of mass momentum. Okay. And now you can find the PCM from just solving the you can also express the PCM in terms of the mass. It's because E1 plus E2 equal to square root S. Okay, so this is the total. So in the center of mass frame, the total momentum is 0. Okay, then that means that E1 and E2. Okay, so here there's no spatial part contribution, and here just have E1 plus E2 square equal to S. Okay, so E1 plus E2 equal to square root S. Okay, and then you can actually solve for the for P by plus M1 square plus M2 square equal to square root S. Okay, so you can now solve the center of mass in terms of S. So so this is a simple equation which you can solve. Okay, so this is a middle school equation, but turns out the result is very simple. Turns out the PCM, the magnitude, okay, when you solve this equation, you find that this is precisely equal to this sigma divided by square root S. Okay, so this is a very beautiful, simple formula. Okay, given by sigma divided by square root S. Or in other words, the sigma can be written in terms of the center mass momentum, the magnitude times the square root S. Okay, times square root S. So now we can simplify that the expression in center of mass frame. So in the center of mass frame, now we have in the center of mass frame, now we have the sigma is equal to, so let me just save the, you should assume that the subscript alpha to beta, the mu, and then divided by 4, center of mass momentum, magnitude of center mass of momentum times square root s. Okay, so we have a very simple formula. Okay. So the most of the time, for most questions we are interested in, as you will see in next lecture, so most questions we are interested in actually corresponding to 2 scattering. So now let's specify to 2 scatterings. So the final state only contain 2 particles. Okay. So in this case we can simplify the d mu. Okay, further simplify d mu. So let's just write down the, so in 2 to 2 scattering, essentially you have some particle come in, say P1, P2, and then you have 2 fellow particle, K1, K2. Okay, and then they're intact. Okay, they're intact. So now let's write down this d mu explicitly for this case. Let's write down d mu explicitly for this case. So the d mu just given by, so P1 plus P2 minus K1 minus K2, and then times D3 K1 divided by 2 pi cube 2 K1 0. Yeah, let's just call Q1 K0 E1 prime, and the D3 K 2 pi cube, then 2 E2 prime. Okay? So the E1 prime and E2 prime, they are just energy for K1 and K2. So E1 prime equal to K1 0. E2 prime. K2. Okay? Yeah, for example, yeah, so right. Yeah, so I will denote the mass for the 2 fellow particles, M1 prime and M2 prime. Okay? So M1 M prime 2 prime will be the mass of the 2 fellow particles. Okay. So before simplify this a little bit further, let us first introduce some notations. Okay. So it's often convenient. So many of you may have already seen this before. Often convenient to introduce the following quantities. So essentially, they characterize all the Lorentz invariant quantities we can build up from P1, P2, K1, K2. Okay, so you can have so-called T is defined to be minus P1 minus K1 square, which is also the same from the momentum conservation, P2 minus K2 square. So U minus P1 minus K2 square, the same, minus P2 minus K1 square. So let me just copy the S, okay? is P1, P2 square. Okay. So these are the quantities which are obviously Lorentz invariant. And they are the Lorentz invariant you can build up. Lorentz invariant quantities you can build up from, say, P1, P2, K1, K2. Okay, so any Lorentz invariant quantities which you can build from those 4 momentum can be expressed in terms of some combinations of STU. Okay. In fact, STU themselves are not independent of each other. There's only 2 independent Lorentz invariants. With momentum conservation, there are only 2 independent Lorentz invariant you can introduce. So S plus T and plus U is actually not independent of each other. You can show. So this again, I give you the exercise for yourself. You can show that, okay? So if you load any of the 2, then you load the S, you load the other one, and anything can be expressed in terms of this these variables. Okay. Any questions? Yes.
So we've written them down as definitions of useful Lorentz invariant quantities.
Yeah.
So how do they correspond to different kinematics, I guess?
What do you mean? How do they?
Different Feynman diagrams.
Oh yeah. Then your Feynman diagrams can be expressed. It can be conveniently expressed in terms of them. Yeah, as we will see in next lecture and in homework. Yeah. Just so this quantity will be this quantity is Lorentz invariant. So that can be conveniently expressed in terms of those quantities. Okay. So now, including the d mu. Okay, d mu. Yeah. So now let's further simplify d mu in the center of mass frame. Okay, so this quantity we can try to simplify further. So we can. Okay, so now let's consider to do this in the center of mass frame. So in the center of mass frame, for 2-to-2 scattering particularly simple, because your incoming particle have the opposite momentum. Okay, so one is PCM, and one will be minus PCM. Okay, and a spatial momentum. And then the final particle, they must also have opposite momentum. Okay, because the total total spatial momentum in the center of mass frame is 0. Okay, so can call this KCM. Then this must be minus KCM. Okay, must be minus KCM. Okay, so for simplicity, let's just call this KCM just K. Okay. So now we can just now let's just with this in mind, let's just look at this d mu. Okay. Look at this d mu. So so there are a few steps. So maybe we don't want to go through all the details of these steps. Let me see. I think, let me just outline some. So I will not, try to only go through some of the steps, not to say doing all the steps. Okay. So now in the center of mass frame, then you find this d mu can be written as So first that this 2 pi falls, and then you have 2 factor of 2 pi cube, and then you cancel. So you have this 2 pi square. Then you have 4 E1 prime, E2 prime. And then you have various delta functions. Okay, so you have K1, you have E1 prime plus E2 prime minus square root S times delta 3 K1 plus K2 and D3 K1 and D3 K2. Okay? So as we said, the K3, they have to be equal and opposite to each other. And then you can just evaluate one delta function, and then the other decay will remain. Okay, the other decay will remain. So essentially, you just have, essentially, we can just forget about this, and then you just have decay. Okay, just have decay. Okay, D3K. And this D3K, you can in turn write it as dk, the magnitude of K and K square, and then the center of mass, solid angle in the center of mass frame. Okay, so this K vector can be decomposed into the angular directions and the magnitude. Okay, and then now both E1 and E2 are expressed in terms of K square plus M1 prime square, and E2 prime equal to K square plus M2 prime square. Okay? So now you can further evaluate this delta function. Okay, now you can further evaluate this delta function because the E1 prime and E2 prime, they're just the functions of magnitude of K square. So you can evaluate this delta function, you have decay over the magnitude of K here. Okay? So you can do that, so I will not go into detail. Okay, I will not go into detail. And so when you do that, when you solve that delta function, okay, and then you find from here, then you find that the final answer is given by, okay, you find the final answer is given by very simple. You find given by K Cm divided by 14 pi square root S d omega center of mass. Okay? And this KCM is defined to be the solution of this equation. So KCM is the solution to E1 prime plus E2 prime equal to square root S. Okay. So again, this is expressed in terms of the S. Okay. So yeah, so through some just technically just evaluate this delta function, and yeah. Okay. Yes.
So are we like when we calculate this classification, are we integrating over all the cases that way we can evaluate all these stuff?
Yeah. So you only evaluate the K around the momentum shell, right? So you can evaluate the delta function because we always have a finite range of K to integrate over. So it doesn't matter. It doesn't matter how wide the range of this, because the non-zero value of d mu is always around those satisfy the momentum conservation. Yeah. Does this answer your question?
I think so. Yeah.
Yeah. Good. Other questions? Yeah. Here I didn't write. Yeah. I think you may wonder here I didn't write the integral sign. How can I just evaluate the delta function? Okay, you can. The reason you can evaluate delta function is just no matter what is the range of decay you integrate over, and you will always evaluate around those delta functions. Okay, and so you can always take care of them. Yeah. Okay. So now if you combine this result And this result, and now we can write a simple expression for d sigma in the center of mass frame. Okay, so if you combine them together, then we find d sigma, d omega center of mass frame is equal to m alpha beta square divided by 64 pi square s and kcm divided by pcm. Okay? And the kcm is the solution to this equation, and the pcm is the solution to this equation. So the pcm is the equation to this equation. Okay, so they are given by the same equation, just you replace the m1, m2 by m1 prime and m2 prime. Okay, so this is the final answer for the differential cross-section for 2-to-2 scattering in the center of mass frame. Okay, in the center of mass frame. And so this is the expression which we will use later for certain, yeah. Do you have any questions? Okay, good. So this concludes the discussion of the cross-section. Okay, so it's finally over. It's finally over. But we have to go through this because this is the kind of things which we compare with experiments. Okay. And in particular, if you calculate the total cross-section, and then you can just integrate this over all the solid angle. Okay. So before now talking about the physical process, there's one more thing we need to consider. So here we consider the initial state to be 2 particles, because we say we don't normally do scattering with more than 2 particles. But there's a lot of situation which still often could happen. Okay, so this is the situation which initial state only have 1 particle. So when your initial state only have 1 particle, what do you have? Yeah, then that corresponds to K. Yeah, so we can still have the situation if you have an unstable particle, then we can decay. And then it's very important for many, in many physical situations to calculate the decay rate. Okay? So now we have P1, say suppose this is the initial momentum, and decay into K1 plus Kn, say final n particles. Okay? So now the initial state only 1 particle, and the final state is still K1, Kn. Okay, alpha. So beta remain the same, but alpha only 1 particle. Okay, and the decay rate is much simpler to define. It's just dp alpha beta dt. Okay, and we don't need to divide by flux all those things. Okay. So now let me explain a little bit. Again, this dp alpha beta, we always mean that the probability of P1 decaying into n fellow particles with, again, particle 1 with range with the decay 1 around K1 and the decay 2 around K2, etc. Okay, and dkn around Kn. So when we write the alpha beta, you should imagine this. We already include that. Okay. So now we can just repeat what we did before. So then this dp alpha beta dt dp alpha beta, then just given by, again, this thing square, beta plus infinity square, and alpha minus infinity square divided by beta and alpha. Okay? And times j from 1 to n, d3 kj divided by cube times v. Okay? So now it's the same thing. Okay, now it's same thing. So the only thing you need to, and the alpha 1, say, is everything else is the same. Okay, so everything else is the same. So you just repeat our previous analysis, which I will not repeat. So the only thing different is just now the initial state is just a single energy. Okay, so you just repeat the whole thing. And then you find, okay, so I will not, then you find d gamma alpha beta equal to dp alpha beta divided by t. And then you find that this is just given by QE1 alpha beta square d mu. Okay, d mu is defined in the same way. Okay, d mu is defined in the same way. Okay, so this is the final answer for the decay case, and the total decay rate will be you integrate just over all momentum. Okay. So the total decay rate so the total decay rate is just gamma total rate. Then gamma is summing over all possible choice of beta, and then you integrate over all momentum. Okay. And the lifetime of the particle tau is just equal to 1 over gamma. Okay. So one difference with the cross-section case. So the cross-section we mentioned before, say it's Lorentz invariant, but decay rate is not, and decay rate does depend on the frame of the particle. Okay, it does depend on the frame of the particle. So so decay rate, yeah. So this lifetime does depend on the frame of the particle. In the right frame of the particle, corresponding to just E1 equal to M1, okay, just equal to mass of the particle. Okay, and so the right frame decay rate is the smallest among all possible decay rate. Okay, because of the time dilation. Okay, that in all other moving frame, because of time dilation, the decay rate become faster. Okay, so that's what you then that the particles moving and they have a longer lifetime. Okay, they have a longer lifetime. So this makes perfect sense. Okay, so any questions on this? Yes.
Is beta a finite
Huh?
Is beta a finite set like that?
Yeah, in general, for the real, you level low, but yeah, beta is what we discover, right? Yeah, we observe what are the decay Fallot products. Yeah, but you can also predict from your theory what are the possible decay. But in real experiment, there always may be some particle we don't know. Yeah, there may be some hidden interactions. Yeah. Other questions? Okay, good. Good. So that finally concludes this discussion of the cross-section and the decay rate. Okay. And now we can study some process. So we only have like 10 minutes to do it. So we will not really be able to do it, just maybe to start it. Okay. So so in general, we will consider 2-2 scatterings. Okay. Okay. In general, we consider 2-2 scatterings. And so one remark to make, and in that case, we have this formula. Okay, we have this very nice formula. Okay. So for particles with spin, okay, say whether spin 1/2 or spin 1, spin 1/2 would be electrons, protons, etc., and spin 1 would be photon. And the scattering amplitude then will depend on the polarization. Of initial and Fallot particles. Okay. So in most experiments, so the initial beam, they are unpolarized. Okay, it's not easy sometimes to do the polarized beam. So initial state, initial beams, unpolarized. Unpolarized means that just corresponding to a superposition of all possible kind of polarizations. Okay, incoherent superposition. And then the final state and the spin polarization of final state normally cannot be detected. Okay, it's a difficult question to detect the polarization of a particle. Okay, and actually, it's not even, say, if you say observe a new particle, it's not even easy to tell whether this particle is a boson or fermion. Okay, so to measure the specific polarization is even harder. Okay. Anyway, so the polarization of Fallot state are normally not detected. So in this case, when we compare with experiment, so when we calculate this kind of cross section, compare with experiment, we should that means that we should to compare with experiment, we should sum over polarizations of final states and average over polarizations of initial state. Okay, so in one, for the final state, we need to sum over them because we need to sum over all possibilities. But for the initial state, all different polarizations contribute, so we need to average over them. Okay, we need to average over them. So for example, if we consider such a process, so a very important process, say in QED is your annihilation of particles. So if you have a particle and an antiparticle, then they can annihilate. When they annihilate, then they annihilate into photon. And then the photon can split into some other particle and antiparticle. Okay, so this is the process of particle A come in. Okay. So this is A bar, this is B, and B bar. Okay, so this is a production, the pair creation of B and B bar from colliding A and its antiparticle. Okay, so in real life, by colliding, say for example, electron plus positron, then you can create many particles. So this is one of the most important way to discover new particles. Okay, many new particles are discovered this way. You just collide the electron and the positron, and then you will be able to create new particles. Okay, for example, you can create muon and anti-muon, and then you can create quarks and anti-quark. Okay, create quark and anti-quark, etc. Okay. So for such a suppose. So in all these cases, both initial and final particles, they're fermions. So you need to specify their polarizations. So this one is supposed to have P1, R1. So here we have P2. Say since this is an antiparticle, let's call it R2 bar. And B would be called, say this is K1, S1. Say this is K2, S2 bar. Okay. And then for the unpolarized process, let me just write down one last formula. So you need to say, suppose the scattering amplitude is m square, okay, so m. And then we need to, for unpolarized process, so we need to average initial spin R1 and average over the final, the R2, okay? And then we need to sum over S1 and sum over S2, okay? And then I have m squared. Okay, so essentially this becomes 1/4, and you sum over all possible spin polarizations of the m squared. Okay, so this is the one we can say compare with experiments. Okay, so next time we will write this down explicitly for this kind of process. Okay, and so let's stop here.